Hey everyone, welcome to the next video. As promised, in this one we're going to be discussing angular momentum. Now, I want to start with a video. Maybe you've all seen something like this before, but I don't know why. Whenever I think of angular momentum, I think of these these squirrels spinning around on bird feeders. Now, I apologize in advance if you don't find this as hilarious as I do, but let's just watch this for a little bit because it's pretty good. Okay. Anyway, that's enough. I think you get the point. And so as hilarious as it might be, what's happening there actually has a lot to do with angular momentum, and we will kind of I think get a clearer picture of that as we proceed through this topic here. So let's get started. The first thing to say is that there are two types of angular momentum, okay? And you could call them orbital and spin angular momentum. So I don't know that this is a common convention. I mean, I know this is done in quantum mechanics a lot, but as far as classical mechanics go, I don't really know that this distinction is made very often. But I think it's a useful one. So let me just define this for you. I'm going to say that the orbital angular momentum is defined to be, and this is defined with a cross product, right? So I'm just going to copy and paste this so I don't have to format the characters too much, but it's the cross product of a position vector and a momentum vector, right? And so you could always write it like this. I think that's probably what I will do. I probably will not write it like this because we know that the momentum now is just the mass times the velocity vector for a given object, and so I think it's just more straightforward and direct to write it like this. And I think we see that the magnitude here is given by, and this just follows from the fact that this is a cross product, right? And so remember, we can just write this as the scalar product RMV, and then tack on a sign of theta, where theta is the angle between the position vector and velocity vector. And remember, this is just a math thing, right? There's no physics here. This is just from our definition of the cross product. So I'm going to just, to specify this, I'm going to say where, as with torque r, and this is the vector r, right, is the vector that takes us from the point about which we'd like to calculate the angular momentum of an object to the point where the object is located. And theta is the angle between the r vector and the v vector. So we're going to look at the dimensions, right? Let me just say orbital and spin angular momentum will actually have the same dimensions, because as we'll see, we can combine these two quantities, much like we could combine rotational kinetic energy and translational kinetic energy if we needed to or wanted to, right? But let me just say this, and we're just going to look at what the dimensions are, as always, right, of each of the terms in the equation. So we'll just put r and v inside square brackets here. Remember, sine of theta is just going to be dimensionless, as always, right? It will always be just a pure number. So what we have is that this is going to be a length times a mass times a length over a time, right? And this works out to be a mass times a length squared over a time. And there are no, well, let me say this. The corresponding SI units are, and I think you can see this, but they will be kilogram meter squared per second, right? And there's no unit that's defined to be a kilogram meter squared per second, so that this is just what we'll write, right? There's no, I think you would call it a derived unit that is used to describe angular momentum. Okay, so then there's that, and so let me just give you an example of what, so an obvious example of an object that has orbital angular momentum could be the Earth as it travels around the sun, right? Because essentially the Earth is translating in space, right? The center of mass of the Earth is tracing out an ellipse, essentially, right? Sort of like a flattened circle around the sun. And so that's why I think it's very natural here to call this orbital angular momentum, because usually it's what we use to describe like something that's orbiting something else. So this doesn't apply just to the Earth, right? Pretty much any planet. The moon has orbital angular momentum as it orbits the Earth, and so on. So, excuse me. What I want to say is that recall that the linear momentum of an object was constant in the absence of external forces. So what I'm going to say is that likewise, the angular momentum of an object is constant in the absence of external torques. And this is just, a continuation of our analogizing between linear motion and rotational motion, right? Okay, so let's look at an example, I guess, of what this looks like here. In this example, we have an object with a mass of 1 kilogram moving in the xy plane with constant velocity vector -5 in the x direction and 0 in the y direction, meters per second, along the line y equals 1 meter. So we want to calculate its angular momentum. And this depends, right? So the value we obtain depends on our choice of origin, right? As with many things in physics, this is going to be like those things. Like I think the big thing was torque, right? I think I hopefully emphasized to you that torque is not meaningful until we assign an axis of rotation, right? And in this case, the same thing goes for this idea of orbital angular momentum. It's not really meaningful until we say the point from which we would like to calculate the orbital angular momentum of an object. So I think very sensibly here we could choose, let me just say, let's choose our origin to be at x, y equals 0, 0, right? What this means is that, because there are two ways I want to do this. I want to do it generally and I want to do it specifically. Let me go with specific first. So what I'll say is that if we think about, or if we calculate the angular momentum when the object is at, and now we'll say x, y equals, let's say And I'll draw a sketch of this too, because I think that would probably be really helpful. But let's say we're going to calculate the angular momentum of the object when it's at the position x is 0, y is 1 meter. This means that our position vector is simply, and remember we're doing this about the origin, right, to the point 0, 1, so our position vector is just 0, 1 meter. But we're going to first do this in terms of magnitude. So let me bring the whiteboard up, and we'll make a quick sketch of the situation, and we will calculate some stuff. Well, just one thing, I guess. Okay, so let's draw our xy axes first. So x, y, and let's say that this is y equals 1. And we're just going to make a sketch of the mass, the object as it's moving. And so what we have is, I'm going to just draw a big circle here to indicate the object. And its velocity vector, right, would look maybe like this. And this is constant. Okay, so remember the position vector takes us from the point about which we'd like to calculate the angular momentum to the location of the object, right, whose angular momentum we'd like to calculate. And so I could say in this case my position vector looks like this, right? And the angle between V and R here is just 90 degrees. And so to figure out the orbital angular momentum for this choice of origin and location of the mass, it just becomes RMV, right, for the magnitude. So let me just do that really quickly. So say with these choices, and I'll just do the magnitude here. We'll say the orbital angular momentum should be RMV sine theta, right? And R is 1 meter, M is 1 kilogram, and V is, well, remember it's the magnitude of V, right? Because we're calculating a magnitude, so this should be 5 meters per second. And then I'll put this in case it wasn't clear, but I'm just going to put in sine of 90 degrees, and that is just 1, of course. So this works out to be 5 kilogram meters squared per second, right? Like that. But, you know, notice that if we had chosen a different origin, right, we wouldn't obtain this same numerical value, because if we had chosen, say, our origin to be like the point 0, -1, right, where x is 0 and y is -1, then we would get double this value, because our r vector would then have magnitude of 2 meters. And so the point is that it's just very important to choose your origin. Now, if you wanted to talk about the direction of this thing, remember that it's determined by the cross product of r and v. And so you could just do the right-hand rule to convince yourself that this should point in the z direction, right? If we want to talk about its vector nature. But we're also going to do this with a cross product. And so, and this is going to be a little more powerful because we're going to do this in general, right? Like, let's say we keep our origin the same, but we want to be more general regarding the object's position. We could write its position vector then as, and I'll write this as, let's say r prime, just to keep it separate from the other r there, but physically it means the same thing, right? And I'm just going to call this x, 1 meter, right? Because we said in the problem statement that it's basically constrained to lie along the line y equals 1. And because we're going to do this as a cross product, I'm going to put 0 in here. Because remember, you have to take a 2-dimensional vector and make it 3-dimensional before doing anything with a cross product. And so this is a vector, of course. So this would tell us then, right? I'm just going to copy and paste this from the other document here, that this would be our result. And I don't want to do the cross product calculation because that is sort of tedious. And you know, if you wanted to, you could even do this with a computer, you know, Wolfram Alpha, Mathematica, MATLAB, whatever, and get the answer really quickly and easily. But if you wanted to calculate it by hand, of course, for fun, you know, feel free to do that. But what you should find is the result is going to be a vector. It's going to be, let me write this as a column vector maybe, where the x component is 0, the y component is 0, and the z component is again 5 kilograms meter per second squared. And so that's the same thing, right? We basically used the magnitudes to calculate this, then used our intuition for the cross product to talk about its direction. And here we just directed it, or we calculated it directly using the cross product, and we find the same thing, which is good, right? So I think that usually this form will be fine for our purposes. I want to say like 9 times out of 10 this will be the one that we use, but don't forget that this is defined by a cross product, and you'll be fine. Okay, so we've talked about orbital angular momentum. Now let's talk about spin angular momentum, right? And so what I'm going to say is spin angular momentum is defined to be, and I'll write L sub s here, and this is just the product of the moment of inertia and the velocity, or sorry, the angular velocity vector of the object, right? And so this is a vector, and you can see that the angular momentum, the spin angular momentum vector, has to point in the same direction as the angular velocity vector, because this is a scalar, right? And furthermore, it's always going to be positive, so we know that these two vectors, the spin angular momentum vector and the angular velocity vector, must point in the same direction. Okay, now let me just say this is usually associated with an object that's spinning about an axis that is on its own body, right? And so let's think about the Earth again, right? So the Earth obviously travels around the sun, but it also spins on its own axis, right? And so we can say, as an example, consider the Earth spinning about its own axis. And this is indeed the reason why we have day and night, right? Because the Earth spins on its own axis. And so I just want to say something conceptually, I guess, about angular momentum in general, right? And I'm going to say that much as linear momentum could be thought of as a measure of an object's tendency to keep moving in a straight line, and this also kind of comes back to Newton's first law, right? We could say that angular momentum could be thought of as a measure of an object's tendency to keep rotating. And so, you know, again, these analogies I think have served us very well, right? Because we so far have seen that they're all holding up very nicely. So I would like to keep encouraging you to think about the analogy between, or the analogies between linear motion and rotational motion. So what we can do with these two quantities is, I would, so I'm not going to talk about the dimensions or the units here, but this, if you check it, you will find that this works out to be the same thing as the other form of angular momentum, right? And this is necessary because we will have occasion to combine these two things. So maybe for you, you could just work out the dimensions and the units on your own, but you should find that they're the same for both forms of angular momentum. Okay, so what I want to say is that this suggests that we could write that the total angular momentum of an object is the vector sum of its spin angular momentum and its orbital angular momentum. So I'll just copy and paste this from the other document here, but I don't think that this should be surprising. I just stated it verbally right, and it's just, I'm going to call the total angular momentum just L with no subscript, and then we just take the vector sum of the orbital angular momentum and the spin angular momentum. And I want to say that this is also conserved in the absence of external torques. Now, the fact that I'm saying external here might suggest to you that with angular momentum, similar to lots of things we've been doing so far, the important thing is to define your system strategically, right? And so you could have, say, internal torques. Like, for instance, think about the Earth, right? Let's say its angular momentum, its total angular momentum is conserved, right? And there's hardly a better example of something whose angular momentum is conserved that I can think of, at least. But, you know, I mean, like, on a day-to-day basis, there's like 7 billion people on this Earth. There's all kinds of internal torques on the Earth, right? But that doesn't change the fact that its angular momentum is conserved, right? I mean, like, you know, stupid example, but I'm applying a torque right now, right? And the Earth's motion is not changing, okay? And I don't know, hopefully this helps you just sort of think more clearly about what the system is, at least in this specific example. And you will have to think about this on this week's homework, right? It's one of the problems. Okay, so let's look at the first example we did, but now let's imagine that the object we were talking about was a rod and it was rotating about its center of mass with this angular velocity, right? So let's compute its total angular momentum. Let me say the purpose is compute the object's total angular momentum now. And so I'm just going to say that the orbital angular momentum is exactly what we found previously, and I'll copy and paste this result so it's here. And let's go with this one. Let's write it as a column vector, and so we could say L naught. No, it's not L naught. It's LO equals this, and this is a vector. Okay, so then we have to think about what its spin angular momentum is. And so to compute the spin angular momentum, we need to first recall that the moment of inertia of a uniform rod, and I should have said it was uniform in the problem statement, but I'm saying that now, so it is uniform. Moment of inertia of a uniform rod is, and this should be, let's say I is, well, let me just say first, rotating about its center of mass, right, because we had two different formulas for the moment of inertia of a rod. And now we can write that this is just 1/12, not 1/2, 1/12 mL squared. So now all we do, right, is we write, well, the spin angular momentum vector is given by the moment of inertia of the rod times its angular velocity vector. And this will be 1/12 mL squared. And I'm going to actually copy and paste this because this is almost what we want here. except remember that this column vector is actually the angular velocity. And so we would have 5 radians per second down here. And then, let's see. Let me just calculate this in Mathematica really quickly for the number. Should be, mass was 1 kilogram, 0.1 squared times 5. Okay, and this is a very small value, probably because L is kind of small and we're squaring it. But this is going to be, let me just use that. And I'm finding it to be about 4.17 times 10 to the negative third kilogram meters per second. Did I mess this up? I'm sorry. I think I messed the units up here. This should be 5 kilogram meters squared per second. As should this. Let me just make sure I didn't make that mistake anywhere else, because I want to... Yeah, I did it. So I first did it down here. Okay. Just bear with me. So this, we said, should be... Oh, why are you being annoying? Okay, meters squared per second, right? And that just comes back to this, right? Kilogram meter squared per second. I apologize for that. Hopefully it wasn't too disruptive. Anyway, so we went through and we calculated the vectors for the spin angular momentum and the orbital angular momentum, right? And notice that these both have only z components. And so this one, remember, is just a result of the fact that we use a cross product to define the orbital angular momentum. And this one is a consequence of the fact that we said that omega was 5 radians per second in the z direction, the positive z direction. Now, just take a second to convince yourself that you understand what this would look like, right? Because this is an important idea, and thinking back to our convention for angular velocity and the sign and all that, remember that this means that as the rod translates, as it moves along the line y equals 1 meter, it's going to be spinning counterclockwise, okay? And so that's sort of the picture you should have in mind of a rod moving to the left along a horizontal line that is spinning counterclockwise. But anyway, excuse me, but to find the total angular momentum, right, we would just say, let me just say this, to find the total angular momentum, we just sum these two results. And so we would find, right, I don't think I'll do the numbers here because this is actually going to be a very small contribution, but we would find that the total angular momentum is just this, I didn't mean for 2 parentheses there, plus this. And there you go. Whatever number you find, I mean, it's going to be the answer there. Cool. So let's talk about the angular impulse momentum theorem, right? And so we're going to think back to Newton's second law for the rotational case now. And we're going to say, thinking back to Newton's second law in rotational form, what we have is we have that the sum of the torques, the vector sum of the torques, right, equals the moment of inertia of an object times its angular acceleration. And so we've, worked with this a bit now. But I want to remind you, right, remember that alpha is the time derivative of omega, right? It's the first derivative of omega with respect to time. And we can call these vectors. And if you're wondering what this looks like, right, taking the time derivative of a vector is not really anything terrible because you just take the time derivative of each of the components. But we're going to switch to focusing on the z component in just a minute here for definiteness. But what I want to say then is that we can rewrite this. We can rewrite the net torque like this. And this just comes from the definition of alpha, right? It being the first time derivative of omega. Okay, so this next part is going to be like a wee bit math heavy, maybe for some of you, but just something I need to say. It's not really anything we'll ever need to use or think about again. I mean, the result is something we'll have to think about again, but the process here is what I'm referring to. So let's say focusing on the z component, if we separate and integrate, so what we're going to do, I'm just going to put this whole thing in here. Okay, so we can take this dt and move it to the left if we don't care about making the mathematicians angry. And I think at this point it's clear that we don't, right? And so now we have this differential expression where we can integrate both sides, right? So we integrate the left-hand side with respect to t, and here I switch the symbol to a script t just to make it clear that the limit of integration is not the same thing as the variable of integration. And then I wrote omega prime over here because I didn't really know what else to write for the same reason. And so what we find is that the integral of the net torque in the z direction over some time interval is simply the change in angular momentum, right? The change in the spin angular momentum. And so what this means, and this is the important part, right? This tells us that if the torque is constant, or we know its average value, because practically speaking, these are kind of the same thing, right? We arrive at, and the equation is, and because this involves a few vectors too, I'm just going to copy and paste it, but it's that the average torque times the time interval over which it's applied equals the change in angular momentum of an object. And we could define this, right? I don't think we'll use this symbol very often, but traditionally I think the change in angular momentum of an object is defined with a big J. And so notice that this, this sort of matches the form of the linear impulse momentum theorem very, very well. And this is something we can appeal to if we want to figure out, mostly what we use it for is to figure out what the average torque was on an object, or I guess knowing the average torque in the time interval, what its change in angular momentum is. So this will be fairly useful, and you'll get some practice applying it. Okay, so let's look at some examples. I mean, I don't really think there's very much more to say about angular momentum. I want to work some examples. I actually have some videos too, some demonstration videos that I want to show you that I think are pretty good. And these will hopefully help convince you that momentum is conserved, and angular momentum is generally conserved in the absence of external torques, and that it is in fact a vector, right? So let's look at some of these demos here. The first one is a pretty typical one that's done in this class. So this professor, right, is going to step onto this turntable that's free to spin. It's probably very close to frictionless, probably oiled up very nicely. And he's going to spin around, and then he's going to basically hold his arms out and then pull them in. And you'll see what effect this has on his angular speed. And the reason, right, that this is happening is because the moment of inertia is changing, right? So if his angular momentum is a constant, but his moment of inertia changes, right, then his angular velocity must also change accordingly, right? Oh wait, I played the wrong part. Okay, I thought I had it set. Okay, here we go. I think he's. Okay, just step on the damn turntable, buddy. Let's see here. Okay, here we go. Exciting, right? So his assistant spins him, right? And now he's changing his moment of inertia because the dumbbells obviously have mass, and he's bringing them, you know, closer to his body and then further out again and so forth. And so you could see that, you know, his angular speed changed. And that's this actually is kind of the paradigm for a pretty typical problem that you'll encounter involving conservation of angular momentum. One we'll actually look at in a few minutes here. And then the other one that maybe is even more interesting is now he's going to have, same guy, he's going to have like a bike wheel that's sort of free to rotate about its own axis. And he's going to spin it and then change its orientation, and you see that he starts to spin, right? I think this is pretty cool. And this is because angular momentum, right, is a vector and it's conserved. And so you can see that, you know, as long as this thing continues to spin, it won't spin forever, obviously, because there is, you know, some internal friction, I'm sure, even though it's not a whole lot. But changing the orientation of it, right, remember the right-hand rule for angular velocity changes the orientation of the angular velocity vector, and thus his angular momentum, because he is essentially in an isolated system. Cool. Okay, I don't know, I thought those were good, and I encourage you to look for more examples online. I'm sure that there are some really good ones out there. But those are the two, I think, most typical ones. So let's look at an example of this, essentially, right, of what we saw in the first video. Now, this is just very general. I didn't put any numbers in except for 9 out of 10, but I think we'll still be able to do a lot with this. So an ice skater is spinning around in a circle with her arms outstretched when she decides to pull them in, hugging her torso, right? Much like he did with the dumbbells. If she is initially spinning with angular speed omega naught, and changing the position of her arms causes the moment of inertia, or her moment of inertia, to change from I naught to I, which is 0.9 times I naught, what is her new angular speed and the corresponding change in her rotational kinetic energy? So let's say conservation of spin angular momentum gives, and we'll say that the initial angular momentum, we're going to focus on the magnitude here, because we're not told, you know, which way she's spinning, and indeed it doesn't really matter if all we care about is the magnitude. So we're just going to say that L initial equals L final. Now, the initial angular momentum that she has is going to be given by the initial moment of inertia times her initial angular speed, right? And her final angular momentum is going to be given by her final moment of inertia times her final angular speed. And so this is just a matter, right, of dividing both sides by I. Well, let me do this first. So remember that I is 0.9 times I naught, right? So she is essentially decreasing her moment of inertia by 10% when she pulls her arms in. Now, I just made these numbers up. I don't know how accurate that is, but it's probably fine to an order of magnitude. But the point still stands, right, is that what we find is the I naughts cancel, because in this equation right here, they're common to both sides, so we just get rid of them. And we find that omega naught equals 0.9 times omega, right? And remember that this is just, you want to write this as a fraction, this is just 9/10. So we find that changing how she holds her arms can increase her angular speed by a factor of 10/9 times omega naught, right? And so her angular speed increases. And that is what we saw with the guy on the turntable with the dumbbells, right? So hopefully this is not shocking now. And I don't know if anybody, like is into ice skating or follows it, then I'm sure you've seen this done many, many times. Okay, cool. So this is just like for a little bit more practice with rotational kinetic energy, but let's figure out what her change in rotational kinetic energy is. So her initial rotational kinetic energy is, we'll say K naught. I'm not going to write an R subscript because I don't want to get bogged down with subscripts, and we're sort of imagining that she remains in place, right? Her center of mass is not moving as this happens. And so we can just write that this is 1/2 I naught omega naught squared. And then her final rotational kinetic energy is, it's just going to be K is 1/2 I omega squared, right? And let's remember what this is. This is 1/2 hang on. So we said 9/10 I naught, right? And then 10/9 omega quantity squared. Now the quantity squared thing is important here, right? Because 10/9 is definitely a different number than 10 squared over 9 squared. Okay, so I'm just gonna have Mathematica simplify this for me, so bear with me for a second, but we have 1/2 times 9/10. Wait, I'm sorry, I should have written omega naught here. Let me just fix that really quickly. 1/2 times 9/10 times I. Incidentally, if you're using Mathematica, and again, I encourage everybody to do this, capital I is actually like a protected variable. It's what they use for the imaginary unit. So you have to use another symbol. I would use like a script I or something like that if I'm typing things into Mathematica, just so you're aware, because I know a few of you are using it, and it could be very confusing if it, I don't know, starts trying to do complex math when you're just calculating stuff. So be aware of that if you're a Mathematica user. Anyway, this is going to work out to be 5/9 I naught omega naught squared. And so the change, and we saw that delta K is K minus K initial, so 1/2 I naught omega naught squared minus, oops, wrong way. Okay, like this. It's 5/9 I naught omega naught squared minus 1/2 I naught omega naught squared. And let me just also do this to get the number. And so it actually works out to be 1/18 I naught omega naught squared. So here we see an example, right, where angular momentum is conserved, but rotational kinetic energy is not. And this is telling in the sense that angular momentum is more generally conserved than rotational kinetic energy, okay? And this was the same thing that I said about momentum, linear momentum, and translational kinetic energy, right? And so this correspondence is just continuing to work, right? Which, I don't know, I think is pretty cool. Okay, anyway. The point, right? The point is, and I really want to stress this because it's important, is that angular momentum is more generally conserved than rotational kinetic energy. So if you're looking at a problem, right, and you feel like you could do it both ways, you could do it with conservation of angular momentum or conservation of rotational kinetic energy, I would say all of the things being equal, go with angular momentum, right? But you'll get some practice with this, and we will work to determine the conditions under which applying conservation of angular momentum is preferable to trying to apply conservation of rotational kinetic energy. And I'll probably do that in a problem-solving video because I do intend to make one for this unit, basically this whole rotational dynamics unit, where we just do lots of problems, get some practice with that. Okay, so I have one more example here, and I think this is a good one because it shows you how it might look when you work with both the orbital and spin angular momentum for a given problem, right? So let me just look at my notes here really quickly. Okay, so let's do this. Well, let me read the problem first. Okay, you're standing on the very edge of a turntable of radius, big R equals 2 meters, and the turntable has a mass of 20 kilograms. So this could be similar to like what the guy was standing on in the video, except this would be, this would have a much larger rate, not a much larger, but like definitely a bit larger of a radius. Anyway, the turntable is not initially rotating, right? But it is free to rotate without friction. So if your mass is 70 kilograms and you throw a ball with mass, and I use script M here because I was running out of M's, but remember that this is definitely not the same symbol as this, right? Anyway, you throw a ball with mass 0.15 kilograms horizontally with initial velocity v0 equals 20 meters per second, directed tangentially to the edge of the turntable. At what angular speed will the turntable begin to spin after the ball has left your hands? So nothing is spinning initially, right? So the initial angular momentum is 0. And this is fine, right? Because I think we had a quiz question, for instance, with linear momentum where there was a system and the initial linear momentum was 0, but after it was still 0, but that doesn't mean that all of the components are 0, is I think what I'm trying to say. So let's make a sketch here because we want to think about what happens after the ball is thrown. Right, I'm going to say the total angular momentum of the system is, and let's just quickly make probably what's going to be a terrible sketch of what's happening here, but it should get the point across. So this is the top view, right, of the turntable, and you're standing, like, say, right here. It has a radius R, and what happens, right, is you throw. And now when I say tangentially, and it doesn't really matter which direction you do this in. Let me see here. I think I want to do it so that the turntable starts to spin counterclockwise. So let's say you throw it like this, right? And this is not you throwing yourself. This is the ball, right? I think that's probably clear to everybody, but so there is angular momentum associated with this, right? This ball now as it has been thrown. And this would just be, let me say something like angular momentum of the ball, right, is just R M, this should be like a script M, V0 sine theta, but sine of theta in this case is just 1, right, because remember that this is a 90-degree angle. And so the magnitude of the momentum of the ball is just R M script M V0, right? Now, after the ball is thrown, right, the turntable is going to start to rotate, like we said, counterclockwise. We'll say this is omega. And we need to figure out the angular speed it starts to spin with, right? So let me go back to the document now. And so now it is just L, and let's say this equals I omega minus Rm V0 sine of 90 degrees, which of course is just I omega minus R v naught. Now, you might be wondering, well, like, how do I know that the turntable is going to start to rotate the way that I said, right, which is counterclockwise as viewed from above? And I know that because I know that the initial angular momentum is 0, right? And so this, remember I counted for the sign here of the angular momentum because it is a vector of the ball with the minus sign here. So I would suggest that you make sure you understand why that is, right? And it just has to do with this stuff that we were saying about, you know, cross products and the vector nature of angular momentum, right? And so there's that. Let me just make sure I did this correctly though. So R cross V should point R cross MV should point up. Oh, you know what would help if I was using my right hand? Okay, so we're good. Okay, because I was confused. Okay, so don't do what I just did. Don't use your left hand. Okay, so you take your right hand, point it in the direction from the center of the circle to the point where the ball has been thrown, right? Then curl your fingers in the fingers of your right hand in the direction of V naught, and your thumb should point, you know, if you're lining your hand up with the screen, so your palm is basically towards the floor, your thumb should point into the screen, right? Then you apply the right hand rule for the angular speed or angular velocity. Let me bring this up again just as I talk about it. So, and you take your right hand, you curl your fingers in the direction of the rotation, and your thumb points toward you, right? If you line up your hand with the screen. I don't know that I can do this. Like, I want to put my hand in front of the camera, but like I don't know that I can do this without contorting my body. So just again, for the angular momentum of the ball, right? Take your hand, your right hand, and hold it so that your palm is pointing towards the floor. Then turn it so that it's pointing, your fingers are pointing in the direction of the vector that takes you from the center of the circle to the point where you are standing, right? Then you curl your fingers in the direction of the initial velocity vector of the ball. Your thumb should be pointing into the screen, right? And then for the angular velocity vector, I can do this, but you just curl your fingers in the direction of the rotation, and your thumb points out of the screen, right, towards your face. Okay. But again, that still might not be clear, so just, you know, get some practice with this. Ask me about it if you're confused. However, you got to work out the confusion if it's there. Anyway, okay. So what we want to do then is we equate the angular momenta, right? And we find, remember, this just looks like L naught equals L. And initially we had 0. And finally, we have I omega minus Rm V naught. And this simply tells us, we're not done yet, of course, but this simply tells us that Rm V naught equals I omega. So that's good. And we need to do one more thing here, I guess, before we take this to completion. We need to figure out what the moment of inertia is here. And so let me say, stopping to compute the moment of inertia, of you yourself, of you, let's just say of you in the turntable. We can approximate the moment of inertia of the turntable probably as just a disk, right? Because remember what we saw in the video, it was basically just like a disk that was suspended a little bit above the floor. So we can just say that the moment of inertia of the turntable was 1/2 big M big R quantity squared. And did I mess up here? I did. I apologize, these should all be script M's. Because remember, this is the ball we're talking about, right? So if anybody's confused about that, that's my bad. These should be script M's. But we will need your mass too, right? So, okay. Anyway, coming back to this, moment of inertia. So we approximate the turntable as a disk, rotating about its center of mass. And then we approximate U as a point mass, right? Because your mass is pretty much concentrated to like a point or a very small area. So I think we can just say that, remember, the moment of inertia for a point mass is just mr squared, right? And so what we find is, upon simplifying this, that the total moment of inertia is this. It's big M over 2 plus little m all times big R squared. Then, and I have to, because I made this mistake in the notes that I prepared too, let me just have the computer solve this for me to make sure it's good. But what we're going to do is we're just going to say, well, now we know what I is, and so we can fully solve this. We can fully solve this equation here. So let me do that. So solve R times and we have big M over 2 plus little m times R squared. We want to solve this for omega. And what we find is that omega equals 2m v naught over big M plus 2 little m big R. And I apparently cannot get this right, but this is also supposed to be a script M. But this should be good. Let me just make sure everything is, I'm paranoid now. I think we're fine. Okay, so let's get a number for this and then we will conclude for today. So what did I say? I said the mass of the ball was 0.15 kilograms. The velocity or the speed is 20 meters per second. Your mass is 70 kilograms. The mass of the turntable is 20 kilograms, and I think that's all we need. We don't need G. Oh, we need R. Okay, so R is 2. So I'm finding a very small angular speed here. But I think this is reasonable. So I'm finding that it starts to spin at about 0.02 radians per second. So quite small, but noticeable, I think. Anyway, that concludes angular momentum. As I said, I do intend to work some more examples for you, and I will give you more homework problems for next week to do with this, because I think I only really gave you like one for this week's assignment, and you're going to need a little more practice than that. But just work through these examples on your own, make sure they make sense, and keep an eye out for when I post the problem-solving video, because we'll do more examples in that, and hopefully this all becomes clear. All right, I will see you in the next video then.